Okay, this is the first video on sequencing series, which is chapter 3 from the year 2 pure textbook. And I'm going to start off with something to get you thinking. These are some kind of slightly strange sequences for you to kind of try and guess what the last term is in each one. I would say you should pause the video and have a think about them. Can you see what's next? And I'll give the answers at the end of the video. Okay, so the first kind of sequence that we need to see and think about is an arithmetic sequence. And I guess the most important thing is to know that the key here is adding. Adding is the key to arithmetic sequences. And what you can see here is we have got a sequence of numbers, 5, 8, 11 and 14. And you might be able to see that what we've got here is a common difference between each term. So we go plus 3, plus 3, plus 3, and this will continue. Now, a little bit of notation here. We're going to label A to be the first term, and this will be true throughout the whole of this chapter. And we're going to label D to be the difference between each term, and you'll often see it called the common difference because each term to the next is the same. They have it in common. And in this particular sequence, you can see that A is equal to 5 and D is equal to 3. And note that D and A can be plus or minus. They're just positive in this case. Okay, so we're going to start to build this up a little bit, and we're going to start to see what we get. I'm going to say, well, the first term in this sequence is equal to 5. The second term, and I'm going to start labeling this A with a little subscript 2. In fact, A1 is the first term, so A or A1 mean the same thing. And we can see that this is equal to 5 plus 3. And over here, I'm going to start writing that in terms of A and D. So the first term is just A, and the second term is A plus D. Now the third term, that is 5 plus 2 times 3, because we've added 3 twice. So that is A plus 2D. And you might be able to see that this continues. Now, the crucial point here is that this number, 2D, is one fewer than the term that we're on. We're on the third term, but we've only added 2 lots of D because we didn't have any at the start. We had 0D here. So if we got to the nth term of this sequence, well, we would have 5 plus, we wouldn't have n lots of 3 added on, we would have 1 fewer, n minus 1 lots of 3. So overall, we can write that an, the nth term, is equal to the first term plus n minus 1 lots of the common difference. And this is our first important formula that we need in this. It is not in the formula book. It's something you have to remember, but just remember, to get to the nth term, you add n minus 1 lots of D on. Okay, now it's time for a little bit of notation. A sequence and a series is, they're very similar, but in the terms of a sequence, you're kind of just saying the sequence of numbers and you put commas in between them. So a sequence of numbers might be 5, 8, 11, 14 that we just saw. And a series is where we add them up. Not really strictly a definition, but you kind of get the idea. A series is if you're adding them up. It's not the end of the world. You get them mixed up a little bit because they're very similar things, but it's really good to try and have consistent notation and to be good with your definitions. As we said, A is the first term, and D is the common difference. And R, which we're going to see when we come to do geometric series later in the chapter, is the common ratio. We're not going to see that today. Well, we might see it today, but not in this particular video. And that is kind of when you're multiplying to get to between terms. This is the nth term. Sometimes you might see U used instead of A, but they kind of mean the same thing. Indeed, like e.g., we could also say that A3 would be the third term. It's just using a subscript to tell you which one. And this is the sum of the first n terms. And so that would be if you had a series and you want to add up the sum of the first n terms. Right, we're going to actually now think about summing up arithmetic terms. We're going to start with Carl Friedrich Gauss's trick for adding up the first 100 terms. So, very much one of the most famous mathematicians. Probably you've all heard of him before. There is an apocryphal tale, i.e. it might not actually be true, as to say that when he was at school, there was a teacher who just wanted to keep the class kind of quiet, and what he said is, okay, add up the first 100 terms. Carl Friedrich Gauss was very young at the time, maybe just the story goes he was only 5 or 6 or something like this, and he had a couple of seconds, thought about it, wrote down the answer and walked up to the front to give the correct answer. So add up the first 100 numbers on the screen. How quickly can you do it? Can you work out a way of doing it like very quickly without just putting them all into a calculator? Or doing them by writing them down in your head, writing them down or thinking in your head? Okay, pause the video, see if you can come up with a good way, and then I'll show what is supposedly the trick that Gauss came up with. Okay, the trick that Gauss supposedly came up with was to write the numbers underneath backwards. So 100 plus 99 plus 98 plus ... plus 3, 2 and 1. And we are trying to work out, so this you can see you'll get 2 lots of the sum from 1 to 100, but what you notice is that if you group these vertically, all of the different pairs add up to the same value. So this is equal to 101 plus 101 plus 101 plus 101 plus 101 plus 101, and what we've got is this, but 100 times, because filling in the gaps 100 times. So we are trying to work out the sum of the first 100 terms in a sequence where A is 1 and D is 1. This is an arithmetic sequence, and we can see that 2 times the first 100 terms added up is going to be 100 multiplied by 101. So 2 times, so S100 is equal to 100 times 101 divided by 2, and you can do that relatively quickly in your head, and you get 5,050. So that's the sum of the first 100 numbers. And you can kind of use this trick with any arithmetic sequence. You can actually use kind of come up with a similar formula to add up the first any number of numbers. So if you have A as 1 and D is equal to 1, you can actually say that Sn is equal to 1/2 times n times n plus 1. You can see that that formula matches that. You may have come across that before for adding up the first n numbers, because it is an arithmetic sequence. A is 1 and D is 1. Okay, so now let's apply this to the arithmetic sequence where A is not 1 and D is not necessarily 1. Well, they can be, but any possible option. Whether or not you believe that Gauss actually did come up with that particular thing is kind of doesn't matter. It's still a really nice story. So we have actually got a formula, and this formula is in the formula book, but we need to be able to prove it, and that is important to know. You have to be able to prove this formula, which is the sum of the first n terms of an arithmetic sequence, which is Sn. You need to be able to prove that. It's important not to get mixed up with the nth term, which is a plus n minus 1 times d, which we came up. This is the nth term. This is the sum of the first n terms. Okay, to do this, we're going to follow a very similar method to what Gauss did. A very similar method to what Gauss did. And that is that if we have the sum of the first n terms of an arithmetic sequence, well, we start writing them out. We have the first term is a. The second term is a plus d. And I'm going to put that in brackets to make it clear that that's the second term. The third term is a plus 2d, because we've added the difference twice. Think 1, 2, 3. And it would carry on, so forth. And the very last term, the nth term, I'm going to write here, would be a plus n minus 1 times d. That would be the nth term. I'm going to add in one term before the nth term, the n minus 1th term, which would be, and I'm going to put that in brackets, a plus n minus 2 times d. Now, this sometimes confuses people, this n minus 2. Well, if you were to think that you were on the 15th term, n minus 1 would be 14, so you want the number before it, n minus 2 would be 13. That's a way to think about it. Just to make this clear, we've got the first, this is the first, this is the second term, this is the third term, this is the n minus 1th term, and this is the nth term here. So we're going to do exactly what Gauss did, and we're going to write it backwards underneath and add it on. So if I write it backwards and add it on, I'm going to plus the nth term. So I'm going to have a plus n minus 1 times d plus the n minus 1th term. That is a plus n minus 2 times d plus the n minus 2nd term. That is a plus n minus 3 times d plus dot 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 plus the first term would have been here, that's a, second term would be here, that's a plus d. And I'm going to add these all together. And in the same way as we got 101 all adding up, I'm going to add them like this. So these terms are added. And what we discover is that these terms are all the same. It does take a couple of seconds to really spot that that is the case, but they are. They all add up to 2a plus n minus 1 times d. That first one you can see is quite easy. A plus a, and you get that. With this one, a plus a, we get 2a. Now we've got n minus 2 lots of d here. Add one more, and we get n minus 1 lots of d. So that is equal to that. That is equal to that. This is equal to this. Again, we get 2a, 2a's. N minus 3d's plus 2 more, we get n minus 1. So we get the same. And all of them in between will also give that. This one would be 2a plus n minus 1d. And this one is going to be 2a plus n minus 1d. And yeah, I'll just remind you, you do need to know this proof. You could be expected to do it in an exam. But if you just remember to write the sequence backwards and add up, that's the trick. There's a lot of writing on the screen, but it's really lots of repetition and follows a very strict pattern. So, what have we got? Well, I have n times this. So, overall, I am going to get that 2 lots of Sn, because we've got 2 still, is equal to n times 2a plus n minus 1 times d, n lots of that, and finally divide by 2 and you get n over 2, 2a plus n minus 1 times d. And that is the proof. That is the whole proof on the screen now. That was a reminder of the other formula. That is the whole proof. It's kind of shown clearly, and that's what you need to write to kind of prove this particular thing. Okay, a quick example to get you started, and then I'm going to ask you to do some questions before we get on some of the harder stuff. So for the arithmetic series 6, 9, 12 and 15, find the 11th term and the sum of the first 11 terms. And I've chosen the same number of terms here because I want to show you that really these equations, you need to use different formulas for these. Okay, so first, the most important thing is that you write down that A is 6 and D is 3, and just have them written down. It's the first thing you do in any question, because there are often marks for them, particularly if you get everything else wrong. Okay, well actually I'm going to put them in my answer because that's where they should be. So A is 6 and D is 3. So I want to find the 11th term. Now I remember that AN is A plus n minus 1D. That is the nth term. So I want to find A11, which is going to be A plus 11 minus 1d, which in this case is 6 plus 10 times 3, so the 11th term would be 36. Okay, for part B, I'm going to need the sum formula, so I want to find the sum of the first 11 terms, but I'm going to remind myself that that is n over 2, 2a plus n minus 1 times d, and that is in the formula book. So S11 is equal to 11 over 2, 2 times 6 plus, in brackets, 11 minus 1 times 3. So what does this equal? Well, you could stick it into the calculator. It's going to have to be a whole number. So even though I've got 11 over 2 there, it should kind of cancel down quite nicely. 11 times 2 is 12 plus 10 times 3 is 30. So we have got 11 times 42 over 2, which is equal to 11 times 21. And that is going to be equal to 231. I check my arithmetic there. 210 plus 21, and it should be 231, which is my final answer. At this point, you need to start just getting to grips with these questions. So I recommend you just do a couple of questions, just a couple of the first questions in each of the exercises before we go on and move on to some of the slightly harder questions and exam questions. So have a go at those. Okay, and unpause the video when you're back. So I'm now going to have a go at a slightly harder question. It's very similar to some of the examples in the textbook on page 64. Find the least value of n for which the arithmetic series exceeds 100. So slightly adjust my grammar there. Exceeds 1000. Okay, so firstly I've got A is equal to 3 and D is equal to 4. Write them down straight away. That's the first thing that I want to do. And I want to know what value of n does Sn first exceed 1000. Well, again, I'm going to remind myself Sn is equal to n over 2, 2a plus n minus 1d. So I want n over 2, 2a plus n minus 1 to be greater than 1000. So let's plug in what we know. We don't know n. So n over 2, we know that then we get 6, because 2 times 3, plus n minus 1, and we've got 4 here, times 4, and that has to be greater than 1000. So let's start making this, and you might look at this and go, oh, well, it looks familiar, I bet I can guess where this is going. Okay, times both sides by 2, n, open brackets, 6 plus, multiply that out, 4n minus 4 is greater than 2000. Simplify this down and expand it out. I've got 2n plus 4n squared. So that's 6 minus 4 is 2. So I get 2n plus 4n squared is greater than 2000. I times both sides by 2, but I could have cancelled it earlier. And so I can divide this all by 2 to get n plus 2n squared is greater than 1000. And rewrite it like this, 2n squared plus n minus 1000 is going to be, needs to be greater than 0. Okay, this is where you stop and you go, this is a quadratic inequality. It's so tempting to forget that when you see a quadratic inequality, when you see something like this, to square root both sides or do something wrong, you have to treat it with respect. Always treat quadratic inequalities with respect. But if I solve equal to 0 this quadratic, I'm perfectly allowed to do that using a calculator, save a bit of time. I can't obviously see how to factorize it, so I think that's okay. And I get this. And what are my values? I get 22.1. So 22.1 is a critical value of this quadratic. And the other one is minus 22.6. Minus 22.6. Those are my two critical values of this inequality. So do a little quick quadratic sketch. I can see that this is around 22. This is around minus 22. Well, n has to be positive because we're talking about a number of terms, so we're not interested in this. N must be greater than 0. And this is going to be, well, we want n to be a whole number. So what are we going to do with 22.1? Well, the idea is that actually that's 22.1 would be, if we allowed kind of steps between whole numbers, that would be when it does exactly equal 1000. But it's never going to exactly equal 1000. So what we actually do is we'll see that it's going to be less than 1000 for n is 22 and greater than 1000 for n is 23. So the answer is n is 23. At this point, and so this is the least value of n for which Sn is greater than 1000. I recommend a quick check of this. So we want to see S22 and we want to calculate S23, and we're hoping that this is just a bit under 1000 and S23 is a bit above 1000. So let's go back to our calculator. Let's go back to this setting and let's type in, using the sum formulas, what these are going to be. Okay, I'm going to use x as n and save a bit of time for my S22 and 23. So I have got n over 2, and I've got 2 times my first term, which is 3, plus x minus 1, which is n minus 1, and that is times 4 because that is the difference between each terms. And I press equal, and I press calc. For x is 22, what do we get? 990. And I press calc for x is 23, and what do I get? 1081. So this was 990, and this is 1081, and we can indeed see that n is 23 is the smallest term for which this exceeds 1000. Okay, and I'm going to say that you should try these questions. They're slightly longer questions. Try another couple of ones from there, but oh, actually I mean 10 to 12 there. So try 9 and 10 from exercise 3A, and then 4 and 10 to 12. Question 13 is a worded question, and that would be a really good question to try out, although we're going to focus on some more worded questions later. And finally, let's finish with what's the answers there. Have you had a thought? Have you worked out any of them? Okay, I want you to have a good think. Okay, and here are the answers. The first one is 31. It's the days, number of days in each month. January, February, March, April, May. Obviously not in a leap year. The answer to this one is E. 1, 2, 3, 4, 5, 6, 7, 8. The first letter. The answer to this one, 1, 2, 3, 4, 5, 6, the number of letters in each name of the numbers. And this last one, pretty tough. Here's the clue. The answer is 8. They are the smallest numbers, the first number appearance of each letter of the alphabet. 1000 is the smallest number when written in English to contain A, B, C, D, E, F, and G. Not really something you could get in an exam, but little nice kind of things to finish off the video there. Okay, next video, I'll be looking at geometric series. There will be me going through some exam questions at some point, but I'm going to stop the video there.